Hello and welcome back to the lab. Today on the bench we have the ZM30U. This unit was teased in a previous video, and we're going to get into the restoration and take care of this bridge. Trying to figure out what to call this thing. So, got a bit of work ahead of us. Most of it is in this area down here. A couple of caps to replace. This is a tag board. There's a whole bunch of resistors hiding underneath this board, so we're actually probably going to pull it out. I'm going to test those resistors, see what happens. These caps need to go. This one's okay to stay. This one's got to go. What else do we have running around in crazy places? These cans will get replaced as well. And we will see if we can't make this unit happy. First, we got to do something about this power cord. This is wildly unsafe and needs to go. So, it looks good. It's kind of flexible, but if you kind of bend the cord, you can actually hear it crunching inside. So, this cord is quite crusty, and it is time for it to be done. And to make this easy and be on camera, away it goes. Oh, God. Yeah, you can see the insulation is just cracking off as I move the cable around. The ground lead's fine. The white and black are not. So this needs to go in very short order. Alright, we have rebuilt the multi-can capacitor section, and we have upgraded the working voltage of the capacitors that were present. We had one 2-section, one 3-section cap. The red pins will be the positive, and then they all have a common that's tied together. These were interesting capacitors as they are case insulated from chassis ground. Now, that matters on one, but not the other. This multi-section can cap that was right here, it was referenced to chassis ground, which actually made introducing this terminal tie point pretty easy. This 22 microfarad capacitor that was in the back was actually insulated from chassis ground and was not part of the ground reference and gets another reference. So the way this is hooked up in circuit, it is not hooked to the chassis. So, what we have done is I have wires coming in, this gray wire and the red wire off of these two capacitors here. This 2.2K resistor actually tested within spec and was fine, but that bridges these 2 points in circuit here. So I moved it off the capacitor and put it up here, and we actually unthreaded the cable out of the wire loom so it's not hanging around to shorten anything out. I'm still waiting on caps for this section, but while we're waiting on the delivery guy, I got the power supply rebuilt. Still not ready to fire this thing up yet. Cannot turn it on quite yet. Need to get a couple of caps in and get them situated before we put some power to this thing and see if there's any life left. Now, let's move over to some of the test equipment and see if this was needed. Okay, these caps are discharged. Everything is turned off. These have not seen power in a number of years, so they're going to be fine, and I'll be able to do this without blowing up my meter. If you do not have a leakage tester and you want to quick and dirty test a capacitor for leakage, it would show up as a resistor. So if we do a 2-wire resistance measurement into the capacitor, it'll actually, you'll watch it charge just like that, and that's charging from the meter current up to the voltage of, well, the test voltage of the meter. Come to think about it, I don't know what the test voltage is on this meter. I should measure that. But we're seeing it slowly climb. 2.2. This is 2.2K, so we're 0.megohm. Sorry, not 2.2K. 222K, 240K. So this section's climbing pretty well. If it stops climbing, things like that, that would indicate leakage current. Let's test the other section of this capacitor. And Well, that's not climbing near as fast. Now, there is a reformation process that's happening that you're watching as this keeps counting up. The capacitor is reforming under the current of the meter. These capacitors have a caustic electrolyte in them, and it likes to eat the insulation layer. So if they haven't seen voltage in a while, they will, for a short period of time, they will draw a lot of current. That's more like it, 1.2 meg. And a physical shock just got this back to rights because I tapped it on the table. Wow. Tap it on the table. 1.4. Tap it on the table. 1 point. Are you going to do it again? Nah, it's happy now. So there was not something, there was definitely something off on that can. Here's the 4-3 section. So we'll test from ground or common to 1 element. Yep, it stopped at 80. So 80K and it's counting down. That's leakage. So this cap needs help, and that needed to be changed. We'll check section 2. It's dead already at this point, but we'll just check it for good measure. This one's counting up, so that section may be healthy. And this one's counting up, so that section might be healthy, but this one definitely has a blown out section too. So both of those caps were not healthy and definitely needed to be changed. Now, one of the reasons for the change is I want to be very gentle with these selenium rectifiers that are back in here. Let's see if I can get a pointing tool. We can get way back in there. So here are the selenium rectifiers, and I do not want to have to change these out unless I absolutely have to. So I want to be as gentle with them as possible. New caps and not overdrawing the selenium. They should be fine for quite some time. I doubt this is a high current device, but we will find that out when we fire it up, because we'll fire it up on the power meter and the isolated power supply. So everything will tell us what is going on. So I guess we are again at a standstill until the delivery man gets here with my package from DigiKey that has the capacitors that I need. About the only other thing I could do right now is work on swapping out this power cord. Use a server power cord that I have laying around. We'll just chop the end off, and that'll have a nice 3-prong plug. I'll have to make up some connections, and we will get that good to go. So, coming along nicely. While we wait, I'm going to give it a good clean. We'll spray it off with alcohol and at least wipe the chassis off. See how it cleans up. I'm really curious. The eye tube's going to tell us a lot. It doesn't look awful, but the dimness of the eye down here is going to tell us quite a bit about how much time is on this unit. So really looking forward to getting some power on this thing and getting it lit up. But gotta wait for the boxes. All right, we've got our new capacitors in. Everything looks good. Our other cap is hiding tucked back behind here. That is hooked up to the amp gain potentiometer, which is fine. Let's see, what else do we have? Everything's good. These caps are replaced. We are ready for fire up. We have a mains lead replaced. In this particular one, the neutral is switched, which is always weird, but that's the way they've done it here. And but the fuse is on the hot side. So it should go hot to fuse to switch. So when you turn the switch off, you turn the chassis off. This is a potential shock hazard wired this way. If something shorts to the chassis, you have mains going onto the chassis, and that can cause some problems in the future. This is not going out to customers. This is a personal unit for myself. So not too worried about that, and if it ever bothers me too much, we'll flip the wiring around. Not a big deal. What else do we have? The capacitors here have been rebuilt. The capacitors down here have also been rebuilt. And we're ready for our first power up. So let's see if we get smoke. We are going to start this on the current limited Variac supply. because these capacitors haven't seen voltage, and this unit hasn't seen voltage in a very long time. And that'll tell us how healthy everything is, and if we wired anything wrong and it's shorted out, which would be a bad day. So let me get that all set up, and I'll bring you guys back. Before we do anything, we're going to move the meter out of lock mode. This pin or not button right here slides up and down, and that locks the meter for transit, and this needs to be out of lock mode before we apply power so it doesn't bend the meter motion. Alright, we'll get the variac turned down, turn it on. Dim bulb tester we're going to set to 2 light bulbs. That'll give me about an amp of AC current. Going to turn this on. Make sure all the tools are away. Nothing's going to fall in the top because I wouldn't want a bright flash and bad things to happen. There's a lot of irreplaceable parts on the top of this unit. This can go from a restoration to terminal quite quickly. But let's give it some voltage. See what we have. Okay, we've come up to about 50 volts. Nothing's happening, which is okay. Drawing about 2 watts. No problem there. Come up some more. .70 volts is drawing about 4 watts. We're starting to get pilot light, so that is good. Internal power is still off. And if we switch this to DC low, we do get meter deflection, which is good. Can zero the meter. Nothing's going to work quite right yet because, let's see, DC low. Not a huge change in wattage. So I'm not unconcerned. Or I am unconcerned with that. Okay, these are fresh capacitors and they don't need to reform, so I am going to bring this up further to about the 117 volt range. So at 108 volts, we're drawing about 10 watts and nothing exciting on the dim bulb tester. All right, I think the power supply is going to be all right, so we're going to bypass the dim bulb tester. Give it full power from the variac. Still on the isolation transformer. And I'm going to bring it up to 119 volts. All right, so it now has full line voltage. This unit may have lots of hours on it. I don't see anything on this shadow angle tube, but I do see the filaments glowing, so I'd be willing to bet you the deflection works. We'll set it to meter. We'll throw a resistor across here, see what happens. Okay, so I am starting to figure out the front panel. In meter mode with DC set to low, this is a low plate voltage across the device under test. We have a 10 ohm power resistor here, and if I adjust this to 0 ohms, it says we are not balanced. So if I bring this over here, right there, at 10 ohms, we get balanced in the meter. So when the bridge is balanced, that means this dial is indicating the test resistance. Now we can also flip over. This will shut down measurement voltage, and if we go to internal here, we will have I have to flip this to internal as well. We'll have a shadow angle that'll close once the bridge is in balance. So this would be an AC test. Now we can find out what that frequency is by hooking a scope up to it. And we'll take a look at that. We'll zoom on into my 7603. And there's our waveform. So, it's rather slow. So it looks like with the oscillator gain all the way up and the amplifier gain all the way up, we are generating just about 500 millivolts of signal. 200 microsecond periods. Actually, just about 200 microsecond periods. And it looks like we have a test frequency right around a kilohertz. A little bit more. It's bouncing around a bit, but pardon the flashing, but we have 1 millisecond periods, which would give us, I believe, 1 kilohertz. Now, for absolute accuracy, this actually, for the meter to be right, this unit needs to be in its case, on its back, and fully warmed up, which is what we are going to do right now. So I'm going to get this put back in its case, going to get this warmed up, let it sit and burn on the bench for a while, make sure we don't have any other electrical problems with it, and then this one might be ready for the lab. One thing to note about this unit is I ran through the manual, and unless I missed something, there are no potentiometers or anything to adjust. There's some front potentiometers, but there's no calibration points in this unit. Some test gear like this has accuracy that is considered intrinsic to the design. And because of the way the unit was designed, that's the accuracy we get. Now, if any of these, we'll shut this off so I can turn it. If any of these resistors have drifted, that'll throw the accuracy off because the accuracy is inherent to this resistor stack and this power resistor in the back. I'm being very careful not to touch it because I just had a vacuum tube piece of equipment warmed up, and I don't want my fingers where the high voltage is. So, if any of these resistors drift, that'll throw the readings off. But all of these resistors are balanced to each other, and I do not want to have to change anything in there if I don't have to. These were the highest quality resistors that could be purchased at the time of manufacture. Unless there's something burned up in here, do not go in here and replace resistors. You'll have a nightmare getting this dial tracking to work again. This is pretty incredible. I have the unit turned on just on its back, and I have the meter dialed. I don't know if you guys will be able to see. You guys can't see, but it is dead center. And this is saying 0010 on the... Or I'm sorry, it's saying 00... This is measuring 1, sorry about that, on the 10x range, so we have to multiply that by 1 to get 10. But that should be 10. Hang on a second. Okay, that makes more sense. I didn't have this knob in the correct position. I had this in the 10 ohms position, so it was reading actually correctly. So we'll put resistance times 10, 1 ohm, to the meter, DC low. Well, the unit was working, and then I moved the range switch. I need to do some cleaning on this range switch. It is not happy because it's saying it's balancing at a kilo ohm, roughly the kilo ohm range. But then if I move it down to the 100 ohm range, it tells me I need to take... So I have a problem in this range switch we got to clean up. So let's see what we can do about that. Okay, a cleaning of the switch pack and also a closer look at this dial configuration. This didn't make a lot of intuitive sense in the beginning, and it makes a lot more sense now. We will unlock the meter, turn on our unit, and with the internal power off, once the meter stabilizes, we will zero out the meter. So we have a 10 ohm resistor as our unknown resistance. Essentially, we have a resistor 1X and a resistor 10X. But then we have, on the bottom side, we have an attenuation factor or a dial setting. So if I kick this over to 1K on the 1X range, and I say give me some DC, it's going to throw me off a little bit. But I can bring the meter back into alignment with the center dial. But this is 0.01 on the 1X, on the 1K range. That means 10 ohms. So if I bring this down a range, it's going to say my resistance, my setting is way too high. I need to bring that down. I'm on the inner 0.1 at 100 is 10 ohms. If I go to the 10 ohm range, I click this over to 1.00 on the 10 ohm range is 10 ohms. If I go to the 1 ohm range, if I go to 10, and a bit and some change, we can get the bridge to balance. So, I had my dial settings set a little wonky, and that is why it was mildly confusing at first. So for now, everything is in balance and working, and I'm going to let this sit on the bench and do some burn-in testing, make sure it works for the long run, and is ready to go. I do wish that we could have some that would be bench ready. This is kind of desktop ready. It has to be in this position to actually use it in its most accurate. I'd like one that could stand up on its other feet and see how that goes. But we will have to see. The manual specifically says if you're going to use the meter, lay it down. If you're going to use the I-tube, you can stand it up. Checking the inductance with my 1 Henry, random 1 Henry inductance standard. This is a little trickier with this unit because you have to adjust the dissipation Q dial at the same time you're adjusting the RLC dial, and then you're adjusting both. You're kind of playing with both at the same time. This is coarse adjustment, fine adjustment for maximum shadow. So if I turn the Q dial, the shadow opens and closes, and I'm looking for maximum open. If I turn the RLC dial, it's very sensitive, so we have a nice null. So that would be right where we'd take the measurement. Now I'm on the inductance 1 on the 1 Henry scale, and I'm at 1.00, so that's correct. And this is saying the Q of this coil is a little over 9.7, so like 9.72. 9.72. And that kind of agrees with my DEER meter. The DEER meter says that coil has a Q of about 10. So everything's in agreement, and I am good with it. Thanks for stopping by the lab and taking a look at this LCR bridge. I hope you found the video entertaining, and hang around. Hit the subscribe button, like, and share. Patrons to the channel help keep the lights on in the lab and assist me for getting videos up to YouTube. Patrons are running about 3 videos ahead right now from the YouTube release. There is nothing behind the paywall, so the support goes directly back into the channel. But we do have some discussions and things like that with Patreons up on that platform. So if you'd like, check that out. And as always, more is on the way, and I will see you in the next video.